All right, I believe I'm recording. Let's take a look at these problems from this function transformations in skill packet number 2. The first 6 problems all are in reference to this same piecewise function. This is just 3 line segments that have been pieced together. The coordinates of the endpoints I've labeled here on the graph, but I've also written those in a table below each function. So recognize that using function notation, that instead of referring to these as the y values, they're referred to as function values. So the x coordinates is the input to the function, the y coordinates is the output of the function. The input of the function is referred to as the domain set. The output of the function is the range set. In problem number 1, we would like to fill in this table for this new function g. Well, this function g is related to this function f through this equation. So let's evaluate g at some input and get at the output. So let's construct this table. If we input a -2 into g, what will the output be? Well, this equation tells us that the output will be f evaluated at -2 plus 1. So I don't have an equation for f, but I do have a table and a graph that when f is evaluated at -2, I know that the output is 0. So for this new function g, when the input is -2, the output is 1. Alright, so let's continue with this table. If I input a value of 0 into this function g, what will I get as an output? Well, the equation tells me that it will be f evaluated at 0 plus 1. This table tells me that f evaluated at 0 is 2, and I know that 2 plus 1 is 3. So I know that when I evaluate this function g at 0, I get a y-coordinate and output of 3. Alright. When I have an input of 2, then here I have at f an input of 2 plus 1. Well, f evaluated at 2, the table tells me that when x is 2, f evaluated at 2 is also 2. And I have that 2 plus 1 is 3. So what this is telling me, when you evaluate g at 2, you get an output of 3. So here's the input of 2, here's an output of 3. And then finally, let's see what happens when g is evaluated at 4. Well, it's also equal to, it is equal to f evaluated at 4 plus 1. And the table tells me that f evaluated at 4 is also 4. And 4 plus 1 is 5. So I know that when g is evaluated at 4, that the output is 5. So that means that this graph is passing through the point 4, 5. Now, we don't want to do that every time for all 6 of these problems. We want to look and see, can we recognize any patterns, any ways that will help us to do this quicker. And what we recognize here is that this collection of x's in this table is the same x's as my next table, as for the table for g. The difference is in the y coordinates, and if we compare the y coordinates, all of these y coordinates have just increased by 1. We had 0 plus 1, which is 1, 2 plus 1, which is 3, 2 plus 1, 3, 4 plus 1, 5. So now if I plot these points on this graph, what kind of observations can we make? If we plot the point -2, 1, it's right here. If we plot the point 0, 3, it's here. 2, 3, it's here. 4, 5, and it's roughly up here. So what we recognize is that this graph has been lifted up 1 unit. If I connect these dots, if I connect these points, we can see that. So the original function f is there in black, and now this new function g is here in blue, and it tells us the relationship between g and f was to take the output of f, to take these y coordinates and add 1. So all of these y coordinates increase by 1, and when we plotted those points, the effect that that has is that to obtain the graph of g, we shift the graph of f up 1 unit. And we're done. Let's move on to number 2. Now, again, rather than going through all of that, we can make a comparison and say that this plus 1 increased the y coordinates by 1. So it's logical to recognize that subtracting 1 is going to take these y coordinates and decrease it by 1. I have a mosquito that's trying to attack me. I'm going to pause. I did not get the mosquito. Alright, maybe it'll come back and I'll try again. So here the x coordinates are staying the same because this minus 1 is affecting the output of the function, not the input. So the -2, the 0, the 2, the 4. Now, if we went in here, let's just do it for 1 and not all of these. Again, if we came in and evaluated this function g to try and determine when the input is -2, what's the output, this equation tells us to input -2 into f and then subtract 1. So I come over here when f evaluated at -2 is 0, and 0 minus 1 is a -1. So I'm not going to do that for each of these because I've already recognized the pattern, and it's quicker just to say 2 minus 1 is 1, 2 minus 1 is 1, 4 minus 1 is 3. So now let's plot these points. -2, -1 is here, 0, 1 is here, 2, 1, roughly right there, 4, 3 is here. Let's connect the points. And we can see that this new graph that's in blue that we have labeled this function g is just a shift down 1 unit. So to obtain the graph of g, we shift the graph of f, which in this problem is serving as our parent function. We shift the graph of f down 1 unit, or one unit down. Alright, and we're done with that. Let's move on to the next one. Now here we see that this one is a little bit different. We're adding 1, but we're adding 1 to the domain. We're adding 1 to the x coordinate, not to the y coordinate, not to the output of the function. If it had said take the output of the function, which is f of x, and then add 1, we've seen that that would be a shift up 1 unit. So here we need to determine what's going to happen here if we evaluate these. Well, let's evaluate this. I'm going to input g at negative 3 and see what the output is. So when x is negative 3, what's the output of g? Well, this equation tells me that let x be negative 3, add 1 to that. Well, negative 3 plus 1 is a negative 2. And if I go to the table, the f evaluated at negative 2 is 0. Okay, so I was a little bit clever in selecting the negative 3 because I wanted to have a value over here. I needed to have this be a value that's in my table. Okay, so let's pick g evaluated at negative 1. Well, if everywhere we see an x, we replace it with negative 1. So this is f evaluated at negative 1 plus 1. Well, what is f evaluated at 0? Our table over here says that the f evaluated at 0 is 2. So this equation is telling us that negative 1 comma 2 is a point that's on the graph of g. If I evaluate g at 1, what would I have? Well, everywhere I see an x, I replace it with the number 1. So I need to use my table on the left here. F of 1 plus 1 is 2, and f evaluated at 2 is 2. So what this equation is telling me that when x is 1, the output of g will be 2. So g is passing through the point 1 comma 2. And over here, let's do it again. If I pick g evaluated at 3, well, right here, hey, I was targeting that 4. X plus 1, x is a 3. 3 plus 1 is 4. F evaluated at 4, I know from this table, is also 4. So g, when x is 3, the output of g is 4. Let's plot these points and see what we observe. Negative 3, 0 is over here on the x-axis. Negative 1, 2 is up here. 1, 2 is right here. And 3, 4 is right here. Well, let's connect these dots. These points, I should say. And what do we observe? Well, something a little bit unexpected. This affecting the domain, this plus 1, actually was a shift to the left. So here's the new graph G. So to obtain this new graph, to obtain the graph of G, we shift the graph of F left 1 unit, or 1 unit to the left. It doesn't matter how you phrase it, as long as you understand it. All right. Need a space there. All right. So let's move on to number 4. Now, let's not go through that. Let's observe that it was unusual in the behavior that even though that this said plus 1, that we actually had a graph that shifted to the left 1. So if it said minus 1, like here, I'm going to expect the graph to shift to the right 1 unit. So if I took the time and plugged in a negative 1, 1, 3, and 5, then what would I get? Well, let's just do one real quick. When it's negative 1, F is, I replace X with negative 1. Negative 1 minus 1 is a negative 2. And F evaluated at negative 2 is 0. And so if you continue doing that, you're going to get these Y values. The Y values are staying the same, and the X values are changing, because the change was inside the parentheses, we were changing the domain before you plugged it into the function. It's bizarre in its behavior that when you plot these points, even though it says -1, it's actually a shift to the right 1 unit. So if we connect these points, these are rigid transformations. When this line segment shifts to the right, all the points shift to the right the same amount. It's a toothpick and not a rubber band. You know, the whole thing is a rigid movement. All right, so we can describe this like we did before, that we have a single transformation to obtain the graph of G. We shift the graph of F right 1 unit, or 1 unit to the right. All right. Now let's move on to number 5. Here we have a negative sign. So F and G are related where the output of G is the opposite of the output of F. So for these input values, -2, 0, 2, and 4, when we evaluate G at -2, this is saying that we're going to replace X with -2, but we're going to take the opposite of what we see over here in the table. Well, the opposite of 0 is still 0. Okay. So if I evaluate G at 0, that's the same as taking the opposite of F evaluated at 0. Well, F evaluated at 0 was 2, and the opposite of 2 is -2. If I evaluate this function G at 2, then I'm replacing X with 2, but I'm taking the opposite of F evaluated at 2. And this table tells me that when F is evaluated at 2, you get 2, and the opposite of 2 is -2. G evaluated at 4 is the opposite of F evaluated at 4. And F evaluated at 4 is +4, and the opposite of +4 is -4. So when we plot these points and connect the points, what kind of observation do we notice about this graph? So -2, 0 is the same point that's on the original graph of F. But 0, -2, it had 0, +2, and now I'm going 0, -2. It had 2, 2, but now I'm going 2, -2. And then 4, -4. 4 and -4. I'm going to have to go a little bit beyond the graph and come down a little bit and just estimate. I'll try to, in the future, to make sure that the graph is large enough that when we do these transformations that the final result is, you know, I don't want you guys to have to extend the X or Y axis. But here we can get away with it. Sorry about that. If well, what do we observe? We observe that this graph is reflected across the x-axis. It's like this x-axis is serving as a mirror, and this graph is looking into the mirror and seeing its own reflection. So it's reflected across the x-axis. So that's how we want to describe it. To obtain the graph of G, reflect the graph of F across, or sometimes you'll see about, the x-axis. So here it was a little bit less bizarre than the addition and subtraction, because this told us to to take the output and multiply it by -1, and we did take the y-coordinate, the output, and we did multiply it by -1. But in changing the sign of the y-coordinate, it's bizarre in the description that that's actually a reflection across the x-axis. Alright, so I'm going to do this problem and then stop the video and do the other problems in blocks. Alright, so here we see, again, we have a reflection. Now last time the reflection, the negative sign was taking the opposite of the output. Here you're taking the opposite of the input before you plug it into the function. So this is not going to be a reflection across the x-axis, and so you might be able to anticipate or guess that it's a reflection across the y-axis. But let's evaluate this function at various points here. So let's see what g evaluated at +2 would be. Well, the equation tells me that g evaluated at x is equal to f evaluated at the opposite of x. So if x is 2, the opposite of 2 is -2, and f evaluated at -2 I can see is 0. So if I plug in a 0, well, the opposite of 0 is 0, and we can see that f evaluated at 0 is 2. G evaluated at -2 is, well, this is take the opposite of x. See, this x and the opposite of x, if this is -2, the opposite of -2 is +2. So I'm just going to save some room and just write that as +2, because -2 and +2 are opposites of each other, and this table tells me that f evaluated at 2 is 2. So when this is -2, this is 2. The opposite of -4 is +4, and f evaluated at +4 is 4. So I can see that the y-coordinates are the same, but the x-coordinates are the opposite of what it was. And so it's doing exactly what it says. Take -1 times all of these x-coordinates. But the description, let's plot the points. 2, 0, 0, 2, -2, 2, -2, 2, and I have made a mistake. Alright. Okay, my mistake wasn't as major as I thought it was. Let's back up. Remember that I'm anticipating that the reflection is going to be about the y-axis. Let's plot these points. I think I plotted one of the points wrong, or I didn't plot it dark enough that I could see it. 2, 0 is right here. And 0, 2, well, it's right there. And -2, 2 is right here. And -4, 4 is right here. So let's connect these. So if we connect these, what do we observe? Well, we observed what we were expecting, that this point -2, 0 got reflected across the y-axis. The x-coordinate changed signs. -2 became +2, and this is 2, 0. Now, a point already on the y-axis, when it spins, when it reflects across the y-axis, it just stays there. This 2, 2 over here becomes a -2, 2, and you were moving to the right 4. Now with the reflection, you're moving to the left 4, and this is -4, 4. So if you stare at it enough, you'll come to the conclusion, yes, this is a reflection, and it's across the y-axis. So we make a statement to obtain the graph. To obtain the graph of G, we reflect the graph of f across, or you'll see about the y-axis. So even though it was the x-coordinate that changed sign, when you think about the x controls left and right from the origin when you're plotting points, and instead of plotting a point that was to the left, you're now plotting a point that's to the right. You have reflected the graph across the y-axis. So what we've graphed in blue is this new graph G. The original graph, the parent function was the graph of f. So those are the first 6 problems. I'm getting a little bit tired. I'll try to do the next ones, and hopefully I'm making sense in my explanation. If not, I'll try again, and I apologize if I'm confusing you. I'm trying to help, so let's hope that I'm doing that.